because you're a couple. Thank you very much, Richard. So yeah, this meeting is being recorded, which will mean that the talks will also be made available via the Life YouTube channel at some point. So just to briefly introduce what's going to happen here before I hand over to Simon and save my voice a little bit. So the schedule today is there's two sessions to this workshop. This is session one, which is aimed at the European time zone speakers, and session two is aimed at the poor US and the North American time zone speakers. And I feel sorry for the Japanese attendees who must be lacking sleep at this point, but well done for being here. So we are going to start off with just a brief welcome, and at 10 past we're going to have our first keynote, which is Richard Watson. In fact, I'm just going to share my screen and show you the schedule. So hopefully you can all see that. So our first speaker is going to be Richard Watson at 10 past 3, who's going to be speaking about an antidote to universal Darwinism. Then we're going to have a brief break because I know it's been a long day, and also it gives a chance for Richard to run over a little bit if he wants. Before we move into the invited talk, so Eva Rendell is going to be speaking on the zone of latent solutions and its role for cultural evolution, which is a topic I'm really, really interested in, which is why I invited Eva. So Eva comes from genuine cultural evolution, not as charlatans. She actually seen animals, so that should be very interesting, and children, which are like animals. And then James Winters, another legitimate cultural evolution researcher, is going to come and speak to us about why is open-ended cumulative culture rare. And at the very end of the session, we're going to have a panel. So all questions will be reserved for the end. Obviously, if there's some questions for Richard during the break, that's fine, as long as Richard's willing to take them. He might want to have a break. But we'll have a half-hour session at the end where we'll do questions and then talk freely. And then session two will kick in after Jessica Flack's keynote, which runs directly after the session one, all the way until the start of session two. We are going to run straight into Mark Badeau's keynote there, but we'll probably start actually a couple of minutes after 6. Mark's going to be speaking about the patent record and cultural evolution, social learning. And then we have Marina Dubova and Nicholas Gutenberg. Marina's going to be talking about open-ended communication learning, and Nicholas is going to be talking about bootstrapping the emergence of diversity. And then we'll have another session, another panel session at the very end there. You are all welcome to stick around for both sessions if you like, or phase in and out. It's totally up to you. Also, there is a Slack for this workshop that you can find on the conference Slack channel. So if you want to comment there after the workshop, we can continue discussions in there. I'll certainly be popping in and out of there to answer any questions anyone has. And my final plug is that I am a co-organizer of a cultural evolution Discord group called Cultural Evolution Online, where we have a weekly journal club / sometimes talk every Friday. If you'd be interested in joining that, Eva's a member, Simon turns up from time to time, and we've critically reviewed one of James Winter's papers, so I'm surprised he turned up. I thought we were very nice though. But if you'd like to join that and talk about cultural evolution with a mix of psychologists, philosophers, animal behaviour people, and economists, anyone who wants to turn up, give me a shout and I will drop an invite link over to you guys. It'd be good to get some more A-Life people over there. Right, I'm going to hand over to Simon to do his bit, and I'm going to massage my throat a little bit.
Cool, thanks, James. I guess just to give a bit more of an overview then of what we're really hoping to achieve with this workshop. So I think, James, this is the 5th time we've run this at A-Life, the SLACE Social Learning Cultural Evolution Workshop. So it's been going now for a few years, which is great. I guess if we just say a little bit then of by social learning, we mean the transfer of information between individuals in a population. And that's definitely something that doesn't just apply to humans in the biological world. It applies to many other animals, and it's something that's well studied in biology, in anthropology, in psychology, in a number of fields. And cultural evolution then builds on social learning. So social learning is the kind of mechanism of how is information transferred between individuals. But then if we take a population level view of that, we can view it as an evolutionary process. So the frequency of different kinds of information does change over time. And in many ways, it seems to follow a process like natural selection. There's innovations, new ideas, new bits of information come into a population. This is a bit like mutation in genetic evolution. And also there does seem to be a selection process because some bits of information seem to spread faster, seem to spread more in the population than others. Others seem to be driven extinct as new variants arise. So in many ways, we can look at the population of information and view that as an evolving population. And that's the idea of cultural evolution. And what I'd really like us to think about in this workshop is, where does A-Life come into this, and particularly what can A-Life offer? And I think on the one hand, perhaps the kind of obvious answer to that is we can do models in A-Life. We can do agent-based models. We can do some quite sophisticated models of social learning and cultural evolution. So we can definitely come in there. But of course, that's also something that's done in other fields like theoretical biology, for example. And I think what we would like to argue is A-Life can actually do more than just modeling work, the kind of modeling work that's done in theoretical biology, but that as A-Lifers, we can take a more abstract view of social learning and not be tied to the particular substrate of human brains or animal brains, which it's implemented in biology. Take a broader perspective, an algorithmic perspective, and that then allows us to ask questions like, well, what can a population that has social learning do that a population that is not able to? What are the benefits of social learning? What does having culture as an evolving system give an organism that organisms that don't have that do not have? And really, I think in A-Life we can take, and we naturally tend towards those higher level questions. And I think this is really where a strong contribution that A-Life can offer to fields like theoretical biology, anthropology, psychology, and so on. So if you do have any thoughts about this, this is something we'd like to pick up on in the discussion session at the end. So if you do have any thoughts about that and what A-Life can offer to our understanding of social learning, evolution of culture, that would be great. Good, so that's what we're kind of hoping to achieve. And with that in mind, I think now it's time to introduce our first speaker, who is Dr. Richard Watson. Richard, I've known for a long time, so I was actually a PhD student of Richard's at the University of Southampton. Richard did his BA and MSc at Sussex University, which of course is a very popular place for artificial life, and particularly that kind of time in the early 90s. That was really where all these ideas were taking off and flourishing. So that must have been a fantastic place to be. Richard then went to the US. He did his PhD at Brandeis University in the Volan Center for Complex Systems. And Richard was working on evolutionary algorithms, evolutionary search, and although he was viewing that from an optimization perspective, he was interested in evolutionary algorithms as optimization tools. Even then, he was taking an algorithmic biology view. So he was particularly interested in what are the benefits of crossover and sex in a population. What's the adaptive advantage of crossover in comparison to a population that only does mutation? And he was coming at that with an algorithmic viewpoint of what can it do in optimization terms, but then he took that knowledge and contributed back into biology about questions and debates there on what's the benefit of sex, why do most organisms have sex. So Richard was becoming more and more interested in biology. He then went on, did his postdoc at Harvard University in the biology department there. He also published his book on compositional evolution, impact of sex, symbiosis and modularity on the gradualist framework. He then moved to the University of Southampton, where he's now an associate professor. He's continued very much to work in biology, but really on big picture thinking. So he's worked a lot now on the extended evolutionary synthesis, and also strongly on the links between processes of learning and evolution. And he was the author of a 2016 paper in Trends in Ecology and Evolution on how can evolution learn. So it's a real pleasure to have Richard here to speak with us. And with that in mind, I'll hand over to you, Richard, if you're able to share your screen.
Thank you so much, Simon. That's the kindest introduction ever in the amount of care that it took. I really appreciate that. Let's click the button for sharing the screen. How's that? Here we go. All right, then I'll begin. So I want to talk about universal Darwinism and scientific worldviews that are supported by it. And I want to challenge the idea that Darwinism is universal and that self-interest is the only possible prime mover. So let's see if I can advance the slide. So the prevailing scientific view is that self-interest and competition is natural and logical. It's natural because it's supported by evolutionary theory and the survival of the fittest, and it's logical because, well, the only logical thing for me to do is what's best for me. This is consistent with a worldview, largely Western, that creates isolation, greed, and unsustainable exploitation that's harmful to us as individuals, as society and a global community, and to other living things in the biosphere. A different worldview, familiar within Eastern traditions, sees a larger tapestry of living things, a harmonious web of life, if you like. In this view, there's no aim to win or outcompete others, only to find harmony with nature, to live with ease and balance, playing a humble role contextualized within the greater whole. Within that worldview, cooperation, synergy, and working together with respect for nature and one another is natural and wise. Everything is connected. Love is the way. Well, unfortunately, that's just mumbo jumbo, isn't it? It's a jungle out there. It's dog eat dog. It's us versus them. You might not like it, but that's the way the world works. Well, hold on a minute, you say. It's not like that. There are many objections to such a position. Nature is full of cooperation. The transitions in individuality are fundamentally a cooperative collective. Humans, despite notable atrocities against one another in nature, are basically peaceful. Neuroscience shows that our brains are wired to be pro-social. And anyway, it's logical to seek social well-being because we're part of a society. Come on, everybody, we can do it. And social organizations that cooperate survive and prosper better than those that don't. So it's perfectly logical. Except that it isn't. The rebuttals from the selfish competition mindset are that whilst nature might have some cooperation in it, cheating is always preferable from the individual's point of view. If there's an action which provides a benefit to the individual, then that's the action that is preferable to the individual. And cooperation is really just a last resort if you can't get away with cheating. Transitions in individuality are explained by selfish genes, given that the components are genetically related. And humans are peaceful only to the extent that we deny our nature through our intellect. Our brains are wired to be nice, perhaps, but only through survival of the fittest, through outcompeting other types. And social well-being is only logical if you take society to be the agent that's doing the maximizing. But it isn't. From the individual's point of view, cheating is still preferable. And pro-social organizations win only through survival of the fittest in competition with other organizations of different structures. It just can't be logical or natural to cooperate unless incentives or selection operate at some other level of organization. And even then, at that level, it's still competition that's the prime mover, not cooperation. Why so sure? Why so absolute about that, despite those observations of the natural world? Well, let's return to the logic and the nature part. The logic is that it can't be rational for me to choose to do something that's not in my interest. If I choose to be pro-social, then that's because it was the best option for me. And if I just like being nice, then it's still what I prefer with respect to my utility function. And if I just can't help it, it's the way I'm built to be nice, well, then it wasn't really a choice. If you accept the concept of individuality and agency and the concept of interest, benefit, utility, or incentive, or any kind of optimization principle, there's no way out of this. Although it might be true that you don't optimize the thing we thought you were supposed to be optimizing, it can't be rational that you don't. And economics and social behavior and evolutionary theory refine the concept of individual, or the maximum, in order to explain the observations as rational under self-interest. What about the nature rather than the logic? Well, competition is the prime mover for all biological adaptation, the differential survival and reproduction of Darwinian units. That's the mechanism that explains all biological adaptation. Dawkins makes the case that natural selection is not only, as a matter of empirical fact, the mechanism that explains all biological adaptation here on Earth, but it's the only logically possible mechanism that could exist anywhere in the universe. But this is not just a claim about exobiology and life on other planets. It articulates a certainty about how things can and cannot work here on Earth. If natural selection doesn't apply, it can't be adapted. nothing above the level of the Darwinian individual can be adapted. There are some circumstances, special circumstances, that might modify what the Darwinian individual is, but whatever it is, above that can't be adapted. So loose social systems, ecosystems, and the biosphere as a whole can't be adapted because natural selection doesn't apply to systems that don't reproduce. Society, ecological communities, and ecosystems might be complicated, but they're not organized for holistic adaptive function. So science and logic say that selfishness is natural and logical, and we're not part of a harmonious web of life. We cannot be part of a harmonious web of life because life isn't an evolutionary unit. So it can't have any adaptive functional organization or any organization at all. It's just an unorganized mess, each fighting for themselves. If Darwinism is universal, there's no mechanisms to support a different conclusion. Now, human selfishness is ancient, existing long before the theory of natural selection or any scientific theory, of course, but I contend that scientific claim that selection is the only possible process of adaptation reinforces and sustains the contemporary Western worldview, justifying and advocating selfishness, exploitation, and discompassion at personal, societal, and global scales. So what if selection was not the only possible process of adaptation? What if universal Darwinism was not correct? If evolution by natural selection is not the only mechanism of adaptive organization possible in the natural world? So that, for example, you didn't have to shoehorn cultural evolution into a Darwinian model. If there's a different mechanism of adaptation, one that does not depend on competition, where selfishness is not the prime mover, then competition and selfishness are no longer natural and logical, and systems that are not evolutionary units might nonetheless be adapted. They might even be harmonious. So that's the big picture about worldviews and how we see everything and create theories that support that, and then the theories support it back again, and the role of universal Darwinism in that worldview. So now I want to introduce a different mechanism, natural induction, that's a different process of adaptation, give a brief overview of a model of evolution by natural induction, and then come back to talk about the consequences for that big picture. So natural induction is a process by which a dynamical system becomes adaptively organized spontaneously. It's natural in so much as it occurs in any dynamical system described by a network of viscoelastic connections that is experiencing episodic exposure to stress or perturbation. Viscoelastic connections are connections that bounce back, but they don't quite bounce back all the way. They give way a little bit under stress. And if you have a system like that that experiences episodic stress, then without being selected or designed for that purpose, it exhibits natural induction. It doesn't require natural selection, although the interaction of natural induction and natural selection is interesting, as we'll see. It doesn't apply to everything, but it applies to some things, and it applies to some things that natural selection does not apply to. I'll claim that it explains how dynamical systems that are not evolutionary units, including ecosystems and societies, can learn, adapt, and solve problems in a quantifiable sense. And it's really not that complicated. It's supported by a well-founded learning theory. It's a type of unsupervised correlation learning familiar in neural networks, based on a principle of entities that fire together, wire together. But in a neural network, that's a rule that Hebb made up. But in dynamical systems, it's just positive feedback on correlations that comes naturally from energy minimization. So to explain how it works, I first want to show that positive feedback on correlations produces adaptation. And in that context, we can pretend that we're talking about a neural network that uses Hebbian learning to learn correlations. A neural network is a type of dynamical system that provides a correlation model, and it can be used as a dynamical system that solves constraints. And when those two different ways of viewing a dynamical system are brought together in a particular way, they produce adaptation by induction. And then I want to show that the positive feedback on correlations that mechanism depends on is completely natural. You don't need to select or design a system to perform such a behavior. And I'll show that by using a model of particles connected by springs that are slightly imperfect and deform under stress. Then I'll briefly introduce a model of evolution by natural induction in an ecosystem and come back to talk about the implications. So first of all, what's induction? It's an inference for the production of general rules from specific examples. Famously, this swan is white, that swan is white, all swans are white. Notice that inductions don't follow logically from the observations, but induction is fundamentally important to any kind of learning. Well, learning without induction means that you do well on the examples you've seen before, but that's just memory or rote learning. Learning with inductions means that you can do well on examples you've seen before and on other novel cases. That's generalization or learning proper, as distinct from rote learning. So what do I mean by natural induction? I mean a natural process that does induction spontaneously, not by design or selection for that function. So brains are evolved to do induction, and machine learning systems are designed to do induction, but natural induction occurs spontaneously in dynamical systems with suitable properties that might include gene regulation networks, protein networks, metabolic networks, ecological networks, and social networks, if they have suitable properties. And it's the change in the hidden organization of a dynamical system through modifying the connections in the network that results indirectly from the pattern of forcing applied to the state variables, the nodes of the network, that results in learning or an increased ability to optimize. So let's look in the details a little bit. Induction requires that you model not just the surface features, but underlying regularities of a data set. Here's a set of 5-bit strings. We're going to model them with a correlation model, because that's the simplest kind of model that can do generalization. A correlation model just models what things go together. So you might notice that in these 5-bit strings, the first 2 bits are positively correlated, as are the middle 2 bits. And the last 2 bits are correlated as well, but they're negatively correlated. When one is up, the other is down. A correlation model records information about multiple patterns and can store and recall multiple patterns. That's called an associative memory. So if we run our dynamical system defined by those associations, it will produce patterns where the first 2 bits are correlated, positively correlated, and the last 2 bits are negatively correlated, etc. And it can generate the 5 patterns that it was trained on, but it can also generate other patterns that have the same association structure, but weren't in the training set. That's the generalization that's crucial. So those 2 ways of viewing a dynamical system as a correlation model. First of all, we may have a set of observations, and for each of those observations, we weaken or strengthen the connections between the components of our dynamical system to represent whether they were positively or negatively correlated and how often. We could do that with Hebbian learning in a Hopfield network, for example. Then we can take that model of the correlations that have been observed and recall patterns from it by setting the state variables to random initial conditions and just running the dynamics of the system, the equation of motion of the system, which will have the effect of locally minimizing the configuration in an energy function, and the local minimum of that energy function will be one of the patterns that we stored. If we repeatedly perturb the state variables and let them relax again, that system of observed correlations will reproduce other local minima in the energy function, Now, the second way of thinking about a dynamical system is as a constraint solver. Here we take the definition of a problem defined as a system of constraints that need to be resolved, and we make weights between the problem variables that say when this variable is positive, this variable should be positive, and when this variable is positive, that variable should be negative. Some of them are strongly connected, some of them are weakly connected. And we randomize the state variables and we run the system as before. And what we get now is not a set of patterns that we stored, but a set of locally optimal solutions to the constraint problem. Now, it was Hopfield that did that first system of Hebbian learning as a dynamical system to form an associative memory. And it was Hopfield and Tank that said, you can set up the weights to represent the constraints of a problem and it gives you solutions to the problem. But he didn't put those 2 things together, those 2 different uses or ways of thinking about dynamical systems. If you put them together in a particular way, you can get a system that does adaptation by induction with a quantifiable sense of improved optimization on hard combinatorial optimization problems. If you're familiar with estimation distribution algorithms and model building optimization algorithms, it's a simple kind of one of those, where you're learning a correlation model of your fitness landscape and then moving in that new space instead of the original space. So it works like this. You set up the constraints to represent the weights to represent the constraints of a problem. You run the system from a random initial condition and it gives you a locally optimal solution. You do that many times from different random initial conditions, it gives you a distribution of locally optimal solutions. And then you use that as the training set to update the weights of the network. And then you run the new network, which has a slightly different energy function. The positive feedback on correlations will be created through that process. So information found by relaxing the state variables is fed back to update the interaction variables. That changes the energy function slightly. It produces a new model that has enlarged attractors for places that you've been to before, forming a memory of its own behavior. And over time, it has the effect of enlarging basins of attraction which are deep, that the system visits often, and excluding the basins of attraction that were shallow and not such good solutions we're minimizing here, such that eventually all the other attractors are gone, and the one attractor that remains in the system attracts from any initial condition the state configuration to one particular point, and that particular point is not arbitrary. It corresponds to the global optimum or a good point in the original energy function. Moreover, it's not just reinforcing solutions that the system has already found, but because generalization is possible, it can also enlarge the basin of attraction for new solutions it hasn't found before, causing the system to go to a better solution than anything that would have been found without learning. Here's an example in a hot field network. Each energy minimizing trajectory bottoms out at a different local optimum. We're interested in those endpoints. Those are the locally optimal minima. If we plot a scatter plot of just those endpoints over 1,000 points, we can see what their distribution looks like. And then when we turn on learning, we see that the endpoints become attracted to a particular configuration that's very low in energy, and it reaches it very quickly. Moreover, you can see that some of those trajectories, I don't know if you can see my mouse pointer, go up in energy and then go down, that the state configuration of the system goes through configurations which are momentarily higher in energy in order to get to state configurations which are lower in energy. I say in order to, as though it's purposeful, because it's not an arbitrary perturbation. This isn't simulated annealing. It's being driven through particular state configurations in order to reach a particular configuration. Now, it's not really going up in energy because the constraints of the problem have changed. It's still going down in energy, but when we read off the quality of that solution in the original constraints, it would have needed to go up in order to get back down to that position. And it not only converges on configurations which are as good as the best thing you ever saw without learning, but better than that, which means it's doing proper optimization and not just reinforcement of something you've already seen. Okay, so that's associative induction or natural induction in a dynamical system with Hebbian learning like a neural network. But the positive feedback on correlations doesn't need any fancy learning mechanism or algorithm. That positive feedback on correlations just means that the more that two things co-occur, the more the connections between them changes in a manner that makes them co-occur more. Such positive feedback occurs spontaneously in any dynamical system described by a network of viscoelastic connections. That just means interactions that give way a little under stress. And when they give way, they oppose less. They don't oppose more, the frustration, they just weaken. That means they become more consistent with the current pattern of forcing determined by the state variables, which makes that pattern more likely to occur again, that combination of variables more likely to co-occur again, which is the positive feedback on correlations that's the basis of Hebbian learning. So we can do that same model, not in a neural network, but in a system of particles connected by springs, where the springs are not perfect. Instead of bouncing back to exactly where they were, they slightly deform, they weaken under stress. And the interactions in those springs, determined by those springs, change in proportion to the stress that they're under. Here, particles can be either up or down, and the long springs want to push them apart. But if two particles are both up or both down, then the spring is under stress, and those are the springs that will weaken. Not all of them, but the ones which are under stress, and the ones which are under stress are the ones which you find at locally optimal configurations. So Chris Buckley can demonstrate that a spring system can do the same kind of learning that a hot field neural network can do. It's a differential easing of frustrations, which accommodates the current configuration. So that means that that loop of relaxing the states, taking the local optima and using them as training samples can be replaced by just relax the interactions. So we have relaxing the state variables and relaxing the interaction variables. That's what a dynamical system does naturally. When we relax the states, we're just following a trajectory which modifies the states given the current weight values in order to minimize an energy function. And when we relax the interactions, we change the weight variables in order to minimize the same energy function given the current values of the states. So differentially minimizing just energy minimization on the variables of a dynamical system is what dynamical systems do naturally. You don't need any special mechanism to do that. But what you do need is pulse. You need the state variables and the weight variables to change on different time scales. If they all change on the same time scale, then it's just a big mess. You can't tell the difference between one parameter and a variable. The state variables need to change quickly and the weight variables need to change slowly. But if you don't pulse it, if you just let the fast variables relax to a local optimum, and then you let the interaction variables relax to that, all they do is enlarge the attractor for whatever local optimum you went to first. It just overfits on that one pattern. And it won't be a particularly good pattern, it's just the first one you went to. But if you repeatedly shock or perturb the state variables to random initial conditions and let them relax again multiple times, such that the system visits a distribution of local optima, and over that time scale, the interactions change slowly, then the interactions can form an associative model of the local optima that enables it to generalize and find better optima. The quality of the improvement is predicted by principles of learning theory and depends on, for example, the learning rate that's given by the ratio of perturbation and relaxation timescales, depends on the availability of a representative sample to learn from. And if it's not pulsed or perturbed, it has only one experience and it can't generalize from one example. And it depends on the inductive bias that you have. Here, we're talking about pairwise connections between variables, which are capable of learning a correlation model. And if the problem you were trying to solve was defined by pairwise constraints, then that's the right kind of inductive bias for solving it. So it isn't magic, but we do understand from machine learning how it works and when it works and what you need to do to make it work better. There's no natural selection here. There's no differential reproduction of entities in a population, not the nodes, not the links, not the network as a whole. It's a differential easing of frustrated relationships in a network, which in Elliott-Sober's terminology is a transformational process, change in the organization of a single system, such as learning. It's not a variational process, i.e. keeping some variants and discarding others, otherwise known as a Darwinian or selectional process. So, Darwinism isn't universal. Natural selection is not the only process capable of producing adaptation spontaneously. It's like the self-organization Alice Stewart Kaufman in dynamical systems, but it's not just order for free. It's a theory of organization that's conditioned by past experience that provides adaptation in the rigorous sense of improving solutions to complex combinatorial optimization problems. So it's a proper theory of self-organization, not just saying order happens for free. Natural induction is an adaptive algorithm that can be realized in many different substrates. It's an associative learning algorithm that learns to resolve constraints between variables, and it can be implemented by Hebbian learning between neurons, which learns to optimize an objective function, or by mechanical viscoelasticity in springs, which minimizes energy better over time, or through self-interest of agents acting on relationships in a society, which will have the effect of increasing collective welfare, or through natural selection on interspecific interactions in an ecosystem, which has the effect of increasing total biomass or improving its ability to find ecological climax communities of high total biomass. But it's still the associative learning algorithm that's doing the work. Even when selection is involved, it's a different adaptive process from natural selection because it applies in systems where selection doesn't. For example, in a system that doesn't reproduce, such as an ecosystem, and because it has different adaptive capabilities. But biology is full of dynamical systems described by networks, and often the links can change over time, including the changing in interaction coefficients changing under natural selection. And if you let natural selection modify the connections of a network, it does so in a manner that eases frustrations between the components and producing the positive feedback on correlations. So now we're ready to look at an example of the interaction of natural selection and natural induction. I've chosen the example of the ecosystem. So here we have a community network of species containing individuals that are evolving under individual level natural selection. And they can change through natural selection the interspecific interaction coefficients, the community matrix of a Lotka-Volterra system. No population of matrices. There's only selection on individual connections. So the three species densities, there are many, but I've only drawn three. Each species density is partly controlled by the resources available to that species and partly controlled by the mutual competition between one species and another. And when we run the Lotka-Volterra dynamics forward through time, we get a climax community that's partly determined by external forcing, the resources available, and partly determined by those competitive interactions. So the pixels represent species densities, and on the top row, the pixels represent the resource availability. And when that's uniform, the species densities become uniform. But if it's not uniform in a particular climate, such resources for some species are available and resources for other species aren't, then some species will be in high density and some species will be in low density. And if those resources go back to being even, it springs back to having even population densities. And if a different climate produces different resources, it models that, but it's still perfectly elastic. Now, if we allow individual selection within each species to favor increased growth rates, because individuals want to maximize their growth rate, if you'll excuse me for personifying them for a moment, one way that they can do that under natural selection is to change the interaction coefficients with other species, and they'll act to reduce competition. Which competition coefficients will be reduced? Well, that will depend on who is in high density at the same time. So if two particular species, X and Y, both have high resources available, they'll be in high density. And that means that it's in X's interest to reduce the competition from Y because Y is in high density, and it's in Y's interest to reduce the competition from X because X is in high density. So it's those interactions that decrease under natural selection. That makes it easier for those two species to co-occur in future, even if they're not forced by those resource patternings. So if we hold the ecosystem in a particular pattern long enough for those interactions to evolve, now when we put the resources back to being even, the species densities stay where they are. They've formed a memory of the pattern that they've been held in. And even if we force it to a different pattern, it resists change. But this isn't just an imprint of a hand into clay. It's an associative memory that can store and recall multiple patterns and generalize, which means it can do adaptation by induction. So let's make it do adaptation by induction. Which problem shall we get it to solve? So we thought we would make it interesting by asking the question, can an ecosystem learn to solve Sudoku? So the initial constraints, the competitive interactions between the species in our ecosystem, represents the rules of Sudoku, such as you can't have two numbers the same in the same row, column, or box. And the fixed species are given as species densities that can't change or have their resource profiles constantly high. So if we start off from a random configuration of species, that's not very good at solving the constraints of Sudoku. If we run the Lotka-Volterra dynamics forward through time, it finds a climax community that's a locally optimal solution. It's not very good. But if we apply regular shocks to the species densities so that it visits random initial conditions and repeatedly relaxes down to a climax community of low energy, that will give us a distribution of locally optimal solutions to the Sudoku puzzle. And over time, as the interactions evolve, it changes the attractors of the system such that now we can start from the same random configuration that we did before, but we go to a different climax community that resolves a lot more of the constraints between the numbers in the boxes, the species in the ecosystem. Then you buy the book of the world's 10 most difficult Sudoku puzzles, and you show that the ecosystem can solve 9 out of 10 of them. Now, ecosystems are not supposed to be able to solve problems because there isn't any selection at the system level because it doesn't reproduce. But it is a dynamical system described by a network of viscoelastic connections. When subject to episodic stress or occasional shock, it adopts adaptive organization, not by natural selection, but by natural induction. This suggests conditions exist where the biosphere could have adaptive organization, even though there's only one biosphere. The Gaia of Lovelock but much more than homeostatic self-regulation. So the interaction between natural selection and natural induction is subtle here. Natural selection explains how a link changed. And none of them would change if there wasn't any natural selection in this model. But natural selection doesn't explain why that link changed or was under pressure to change and not some other. And more specifically, it doesn't explain why the links that were under pressure to change were exactly those required to increase long-term collective welfare. It's natural induction at the higher level of organization that explains the structure of the selection on the individual components at the lower level of organization. This view is compatible with natural selection at the lower level. We can think of the individuals within each species as competing with others to be the least frustrated out of short-term self-interest to maximize their own individual growth. But that's not the adaptive algorithm that's going on at level L+1. That's the associative induction algorithm. So now I want to briefly return to talk about those big picture implications. First, the same principles extend to social organizations. If each individual in a social organization changes their friendships with others to maximize individual utility, and the system experiences episodic stress or occasional perturbations, then the organization of those connections increases long-term collective welfare. That means a society can have adaptive organization without top-down governance, the invisible hand of Adam Smith, if you like, but much more than simply finding the local Nash equilibrium. It also applies to gene regulation network, and I've done a lot of work on that with my students and postdocs. Here, the episodic stress is the life cycle. Fast variables change over developmental time, over evolutionary time. The configuration of the developmental process is evolving. And that increases long-term fitness, enabling the evolution of evolvability without higher level selection. It's the evolution of epigenetic structure that models the environment, a la Rupert Riedel, but in a rigorous sense that improves adaptive evolvability, not just mirroring the environment or modularity. Now, all of this has a flavor of connections and connectedness. Adaptation by natural induction isn't driven by differential survival and reproduction of entities at the level L+1. It's driven by the differential easing of relationships between entities, and the systemic intelligence that results, that knows the answer to the Sudoku puzzle from past experience, is held not in the parts, but in the conditioned relationships between the parts. That's not about competition, survival, and selfishness. It's about connectedness, organization, and relationships. So the prime movers of natural selection are differential survival and reproduction. Some win, some lose, some are retained, some are discarded. But the prime mover of natural induction is the differential easing of frustrations. It's transformational change. Those two different prime movers, if you were interested in improving the ability of those processes to do adaptation, you'd want to do different things. Adaptation under natural selection is supported by random variation, free competition, allowing some to win and others to lose. You wouldn't want to regulate things too much. A laissez-faire economics would be better. No passengers, no handouts, no compassion, hence the virtues of selfishness. But adaptation under natural induction is supported by valuing relationships, because they're the weights where systemic intelligence is held. You need to let them mature with experience. They can't be rigid and unchanging like a top-down governance, but they also can't be a laissez-faire free market where you don't allow any relationships to build up. Creating good opportunities for varied experience is also essential. That's the episodic stress or perturbation, because you can't learn a good model from one experience. And that suggests that a sustained pressure for increased profit on a system, or performance indicators, or cost reduction or throughput, destroys or reduces systemic knowledge. It works against systemic intelligence because it holds a system in one state, and you'll get a response, but it'll cause the interactions within the system to fit to that one experience in the same way that overfitting to a single or specific data reduces generalization in a learning system. So what's happened to the logic of self-interest? I argued earlier that you can't really get away from the what's in it for me. It's unavoidable as soon as you define an individual with a utility function. But under natural induction, individuality is a fluid thing, if it's a thing at all. In social networks, de-stressing relationships changes actions from being compatible with short-term self-interest to being compatible with long-term collective interest. And in evolving networks, as relationships evolve, units become less of an individual, they become de-Darwinized, and the system becomes more of an individual or Darwinized at a higher level of organization. Individuality is all relative and contextual. The relationships define who the individual is and what they want. There is no individual except in relation to others. So under natural induction, it doesn't say that all life is lovely and harmonious. The principles of learning theory tell us what conditions will enhance systemic intelligence, when it'll work and when it won't. But it is compatible with a worldview that sees our relationships with one another and with nature, not just as resources and opportunities to benefit ourselves, but as connections that hold collective knowledge accumulated by experience. It's those relationships that make the whole smarter than the sum of the parts. Perhaps such a perspective encourages a worldview where we want to treat our relationships with each other and nature with some suitable reverence. Dare I talk about love? When we form relationships with others, evolutionarily or personally, our future options are changed. Those relationships cause us to do something different. They change our incentives, they change the options available to us, with the consequence that sometimes we're caused to do something that we don't want to do. This is not merely a regrettable obstacle, however. The organization of those relationships can be adaptively organized such that the new options or incentives they present cause self-interested individuals to act in better alignment with long-term collective interest. And a word people sometimes use to describe relationships that cause us to serve something other than ourselves is love. Not the sentimental or brain chemistry kind, the kind that does real work, the kind that makes us do things we don't want to do, the kind that makes us part of something greater than we are as individuals. An antidote to universal Darwinism offers perhaps a scientific framework that recognizes that selfishness and competition are not the sole prime movers, and naturalizes an incentive to ask, what do we know of each other, rather than what's in it for me? There we are. I want to thank James and Simon for the invitation and all of you for your time. And there's a little message there to all of you. I'll come back to the viewing the screen. How did I do with timing?
Great, thanks a lot, Richard. You're absolutely perfect. So time is 10 to 4, so that's absolutely perfect. So the plan now is we will take a 10-minute break at the workshop because it is important that we have time for breaks. So we'll take a 10-minute break now and resume at 4 o'clock, and then we'll have a panel discussion after the next 2 talks. And there's certainly a lot of things I think that we can draw on from Richard's talk for that panel discussion. So thank you very much, Richard.
You're welcome. Thank you.
If anyone doesn't want to go for a break and you're fine, you're more than welcome to use this space to chat, either in the chat or, unmuting yourself. That's totally up to you. I'm going to go make something for my throat. So back in a mo. This break was just for me more than anything else.
Thanks, James.
Thanks very much, Richard. That was really great.
Hi, Richard. Thanks for your talk. Is it all right if I ask a question?
Yes, please. Thanks, Stavros.
So I want to ask, going back to sort of the mechanism of learning for the dynamical systems you mentioned, is it the case that it's just the frequency with which each local attractor is encountered with each relaxation that is then amplified by this process, or does it is it also the like how the magnitude, let's say, of the quality of that attractor as well?
Yeah, good question. So it's closer to the frequency. More exactly, it's the amount of time you spend at the attractor. But the quality and that property are positively correlated. Specifically, in a system where the energy function is built out of a sum of pairwise interactions, that places a limit on the slope of the energy function. It can't be arbitrarily steep. If it could be arbitrarily steep, then you could have little tiny basins that were really, really deep. They'd be really, really good, but you'd almost never go there. But if there's a limit on the slope, then the depth of attractors is positively correlated with the width of attractors. So it makes it much more likely that wherever you start, if you start in a random position, you'll end up in a tractor which is generally good. It's the same way that simulated annealing or a Boltzmann machine finds good solutions more often than it finds bad solutions. So if you have a perturbation set up that you visit a distribution of those attractors, first of all, you're visiting locally optimal solutions, which is better than random configurations anyway. Secondly, you're more likely to spend more time at good ones than at bad ones. And the more time you spend in a configuration, the more you learn it, the more it increases the basin for that configuration.
Great, thank you very much.
Cool. Don't know about you, but it's bloody hot here.
Hi, Richard.
Hi, Alistair.
I've got a question for you. I'm still getting my head around it, but
I can hear you, but you're in the dark. Yeah.
I'm in the dark. Oh, right, there I am.
There you are.
Hopefully that's better.
Yeah,
Am I right in thinking you're saying that if you have natural selection operating at level L, that you will have natural induction operating at L+1, or is it that it can happen?
I can tell you the conditions.
Okay.
The conditions are that natural selection operates on interactions that control the correlation of the state variables. Right? So if you had natural selection on species in an ecosystem, but all they did was change their independent growth rates, then you wouldn't get natural induction. If they change the interspecific competition coefficients, then that's necessary, but still not sufficient. The other thing you need is that shocks or perturbations that causes the system to visit a distribution of local optima. Then the system will necessarily form an associative memory of the places that it's been. And because of the property I was just saying to Stavros, that will cause it to visit good places more often over time. And generalization causes it to find configurations which are better than any that it's visited before. So the conditions are the same as they are for a learning neural network, right? Learning isn't magic. You have to have good data, which you get from the perturbations. You have to have an appropriate inductive bias, because you can't do induction without an inductive bias. Here it's just that everything's based on correlations. And you have to be able to modify the parameters of your model. Otherwise, you can't learn anything. So the same conditions that for learning neural network as it is for natural induction, if those conditions are met in a dynamical system of any kind, including a system where the changes are happening by natural selection, then you'll get natural induction.
So I was wondering about the open-endedness of this. In a Hopfield network, if you manage to find some states that weren't initially encoded or learnt, then you can add that into the mix, but you'll have a finite number of those.
Yeah.
So the process will run for a while and then stop. But is natural induction in combination with natural selection, I guess with the drive for any open-endedness within it be from the natural selection side, but natural induction would still be operating? Or?
There's two ways to answer that, one which is disappointing and one which is more interesting.
Right.
The disappointing one is, well, it's just a dynamical system contracting in phase space over time. So at first, it's relatively free to change given by the constraints that you put between the state variables. And that only gets worse over time, that as the interactions change, they become more consistent with one another, and the number of places that the system can go reduces, not increases. Mm-hmm. However, if you look at the scale of the individual units, they are getting simpler over time. They change their interactions to ease frustrations with others and make their life simpler. But the ecosystem started off as being something where there weren't any units at that level of organization. There wasn't any adaptive organization at that level. And through induction, there becomes adaptive organization at a higher level of organization. So although the lower level evolutionary units get simpler over time, that creates structure in the higher level system that wasn't there before. Now, if you like, you could say, but if I was looking at the higher level system from the beginning, then that used to be able to do anything and now it can do less. But if you were looking at the individual components, then you'd say, well, that used to be just a mess and now it has something adaptive in it at a high level organization that wasn't there before.
So it's pretty something else. another question or two, if I might sneak them in. You talked about natural selection at level L, natural induction at L+1.
Yeah.
Does that have any implication for L+2, and what on earth is going on below L?
So yeah, good. So I did a paper with Christoph Thies about multi-level stuff and how that fits in with evolutionary transitions in individuality. So the natural induction is a process potentially for organizing co-variation, co-selection, and co-inheritance that creates a new Darwinian unit at a high level of organization that can then participate in evolving interactions with other units at that level of organization and does induction at the next level and so on.
Okay.
And then you can think about it backwards. When you go backwards back to origin of life questions, you're asking questions like, was it replicator first, which requires you to start with natural selection, or metabolism first, which is much more compatible with natural induction. But we're interested in how can you get from one to the other? How can you have both those stories be compatible and work together with each other? So we talk about that in that.
Thank you.
So on the open-endedness point, I was just curious, like I think if I understand the natural induction, the stuff at the level of correlation learning, it requires the interactions be symmetric. So that if I have one agent change how it benefits or harms another, it has to be mutual. But if you have anti-symmetric terms, that should drive chaos. That should basically drive destabilization. And that kind of thing is a standard mechanism for open-endedness in like predator-prey, competitive cascades, red queen stuff and things like that. It might not be harmonious. I mean, it's anti-harmonious in a way, but it's a kind of standard thing also in like curiosity, intrinsic motivations, that you have two parts of the system that are actively trying to do things incompatible with each other becoming stable.
Yeah, great. So the models that I've done so far, apart from one, have all done symmetric interactions. When you have symmetric interactions, the behavior of the system is described by an energy function that has fixed point attractors. And when they're not symmetric, that's not guaranteed. You can have cycles and chaos and all sorts of anything could happen. However, when you apply Hebbian changes to interactions, which weren't originally symmetric, the Hebbian changes, the change of the deltas, are symmetric. And as the deltas accumulate over time, they calm down the dynamics of the system. So if it's still the case that to the extent that you minimize energy at all, that there's anything progressive about the dynamics of the system, there might be other swirl going on as well. But to the extent that there's something systematic happening, the correlation learning will make you do that more often.
So I guess you can't impose anti-symmetricity, because if you did, the Hebbian updates would just be 0.
No, the updates, let's see, what do we mean by impose it? So
like if you have a constraint that Wij has to equal negative Wji always, that you aren't allowed to actually have them.
Yeah, you have to be able to change them.
Well, like you could change them, but you have to change them in the anti-symmetric way, or a way that's projected onto the anti-symmetric space. Then I guess the Hebbian update is just 0.
Yeah.
So that's a problem. You'd need a different update rule too.
That would be. I don't know why one would assume that such a constraint would exist, but if it did, that would be the correct conclusion, I think. Yeah.
I mean, like you could do it in zero-sum cases, right? Where if I'm going to, it's a bit of a weird zero-sum, because it's not like the interactions are not like saying, I take resources so you don't have them. It's like if I benefit you, you have to hurt me. Or so it's like I can only benefit you by giving you a subsidy, right? So if you had like a system of subsidies, it would have that property where if I want to pay someone to do something else, I lose that money. And then the interactions have to be, at least for that variable, have to be anti-symmetric.
Cool. Yes, good question. Thank you.
Hi, Richard. A great talk. Thank you.
Thank you.
I had actually a question that is a bit related to or follow up to Alistair's. You know, the last one where you said two different systems, you know, at level L1 interacting, they could create an L2, you know, new organization at L2 level. But how about, you know, the interactions between those systems could change the L1 organization of each system? So you know, you were talking about the shrinking of the options, like, you know, stabilization, but the system is shaken by another one is destabilized, and that could lead to a different, you know, adaptation of the organism.
Yeah, yeah. So interesting. So the work that I know of that relates to that most directly is Friston's work, Carl Friston's work on the free energy principle, right? So if we think about there being an environment out there and an agent that's interacting with it, we can think of the agent as inducing a model of what's going on in the environment. But if the thing that's out there in the world is also an agent that's modeling it, then more interesting things can happen. Yeah. That's good. And especially if one of those systems is capable of learning a higher order model than the other, then that asymmetry would be interesting too. Yeah.
And the other question is, I've been looking at, you put some references on your slides, and I've been looking for them online. Cannot really find them.
Yeah, they're all on Scholar. So I given James the slides, which has the reference list there, and I flashed them up so that you could pause the video if you only had the video and not the slides.
Okay.
But yes, they should be available afterwards, and they're all on Scholar.
Okay, thanks.
Well, except the ones which are in prep.
Yeah, I'll, hopefully that will be updated today or tomorrow with all the slides.
Brilliant, thanks, James.
Depends when I can harass my PhD student to do it. Okay, so right, I am going to move on now to our next talk. So thank you very much, Richard. I imagine there's going to be lots more questions as well later if you're able to stay around. But if you aren't, I do understand. But if you are, that'd be great. So our next talk is an invited talk. It's Eva Endal, who I know from the Cultural Evolution Discord and just generally being around the cultural evolution world. She's a name that crops up quite often because she does really, really cool work. So at the moment, I believe Eva is currently at St Andrews still, School of Psychology. She describes herself as a developmental psychologist interested in evolution and development of social and individual learning, innovation, causal reasoning, problem solving, and executive functions. And Eva's worked with both primates and humans, most recently children. As a father, I am sorry. I mean, I couldn't be paid to do experiments with children. So Eva is going to talk today about the zone of latent solutions and its role in cultural evolution. So over to you, Eva.
Great, thank you very much, James, for inviting me and asking me to give a brief introduction to the zone of latent solution hypothesis, or SLACE hypothesis. Can you see that okay? Yeah?
Yep, can see that.
Okay, great. Super, okay, I'll start right away. So this zone of latent solutions, or SLACE hypothesis, has been developed to explain differences between the cultures of modern humans on the one hand and the cultures of non-human animals, specifically non-human great apes on the other hand. And this hypothesis is to date the most parsimonious approach of explaining non-human animal cultures, and it differentiates those clearly from modern human culture. And one of the reasons I think this hypothesis could be interesting to some of you is because it illustrates how cultures can evolve in the absence of what some might call action copying or imitation, or in general just high fidelity copying as humans possess it. So this is largely the brainchild of one of my former PhD supervisors, Dr. Claudio Tegne. This hypothesis has been first formulated in 2009 and is constantly being revised, and the most recent update can be found in this 2020 paper. So first, I would like to give a definition of culture as I use it here. So with culture, I mean behavior patterns for whose form or frequency in the population social learning of any variant plays a role. And these behavior patterns can differ between populations, as you can see on this quite coarse map of human cultures in the world. So when we move over to great ape cultures, here I use the chimps as an example, you can see some similarities in these patterns. So here you can see 6 chimpanzee populations and their patterns of cultural traits that they show. And the idea is that if I take a chimpanzee and tell you what cultural behaviors she can show and which she doesn't show, you would be able with this map here to tell me which which population this chimp would belong to. So much like in the human case. So superficially, there's a similarity between modern human cultures and the great ape cultures, but the ZLS hypothesis states that the underlying workings which produce these patterns are quite different. And I'll try to briefly explain to you how this hypothesis explains these differences. So let's start with human culture. Modern human culture, as probably all of you know, is very often cumulative. And with this, I mean that this phenomenon that cultural traits like behavior, artifacts, knowledge, language evolve over generations. And sometimes these traits can reach levels of complexity or arbitrariness or opaqueness, which cannot be invented by a single individual within their lifetime anymore. So these products of this cumulative cultural process can only be acquired through high fidelity copying, through action copying, because you can't invent them by yourself anymore. And that's why these behavioral forms have been called copying dependent forms. In contrast, when we move to the cultural traits that we see in non-human animals, here I specifically focus on the great apes. For example, nutcracking in chimpanzees or termite fishing. These behaviors have been called cultural because they have been observed in some populations, but not in others. So the ZLS hypothesis claims, and there's also accumulating empirical evidence, that these cultural traits do not need this action copying in order to be learned by a naive individual. Instead, these behaviors can be invented by any able-bodied member of the population, given that they are in the correct motivational and developmental stage. So these behaviors are not copying dependent forms, but they are latent solutions. They are part of this zone of latent solutions of behaviors that you can invent individually. Humans also have a ZLS. And the question obviously is whether chimps and other animals also have cumulative culture. The humans, because of their capacity for high fidelity action copying, have been able to go beyond their zone of latent solutions. So they have been labeled as having a ZLS plus culture. And the claim is that non-human animals seem to be restricted to these ZLS only cultures. However, we are still talking about cultures, so social learning is still involved. So how would that look like? The claim is here that non-copying forms of social learning, so local enhancement, for example, stimulus enhancement or emulation learning are at play here and can affect the likelihood of an individual reinventing a certain cultural trait. A brief example, imagine you have a naive chimpanzee here on the left and another one sitting at a termite mound using sticks to fish for termites. So, and the mere presence of this chimpanzee at the termite mound attracts the attention of this naive individual. And it will go to that location that is called local enhancement, and its attention will also be drawn to the tools and the termite mound itself. So that is stimulus enhancement. And this social influence basically facilitates the individual reinvention. The actual action, which is like using a stick to perforate the mound and then a finer stick to fish for the termites, is not copied, but is actually reinvented by the chimp. It's basically reinventing the wheel case. And this has been called, so this whole process has been called a socially mediated re-innovation. So an individual re-innovation, which is facilitated through these low-level, non-copying forms of social learning. There is no transmission of know-how, so there is no action copying involved. It can look like this from the surface, but actually there is evidence showing that this is not the case. Chimps are not very, they don't engage very often in action copying. So what are the implications of these ZLS only cultures? So these non-copying forms of social learning can affect or facilitate the frequency of cultural traits in a population, and also how quickly they spread through the population. So if I have a chimpanzee fishing for termites, this facilitates or increases the likelihood of other chimpanzees going there and inventing the trait by themselves, and so the spread through the population. Also, these population differences in the patterns of cultural traits, which I showed you earlier and again here, these can be explained these can occur if a population only has these non-copying forms of social learning. This has actually been shown also in some modeling work by Claudio Tenier and his colleagues. They had an individual-based model where action copying was basically not allowed for the agents. There was just this low-level social learning and this individual reinvention, and they were able, as you can see here, to produce these populations of simulated great apes, so to say, and to have these different patterns between the different populations. So action copying is not needed to produce these cultural patterns here. And lastly, because this is a form of individuals reinventing behaviors which are within their zone of latent solutions, the behavioral forms that we can see within a population remain highly similar across the individuals. Like in modern human cultures, there is like information copying or information transmission from one individual to the next, and that allows copying errors to accumulate. It's like the game telephone. You have an input at the first generation, and in the last generation, you can get something wildly different. And that is not the case in these ZLS only cultures. So the termite fishing will always be highly similar in all the individuals in a population. I will end with the question that is very interesting, obviously, for the people like me, whether these ZLS only cultures can produce cumulative culture. Obviously, this wouldn't be cumulative culture based on action copying, but cumulative culture based on these lower level social learning mechanisms. And there are two points which I will just briefly point out. One is, or one possibility is the presence of culture dependent traits. So not copying dependent, but just generally culture dependent. This could be knowledge, or these could be traits within the ZLS, which are individually, or which can be innovated individually, but are quite unlikely to be innovated. For example, knowledge about a very well hidden water hole. It could be that you need some low-level social learning from others to actually acquire that knowledge. And another example would be stepwise traditions. These are basically latent solutions which are based on the presence of another latent solutions. Quick example, one cultural trait in chimpanzees is using a stone as a wedge for a stone anvil for nut cracking. And you can only use that stone as a wedge if you have previously acquired the trait nut cracking. So there is some kind of leveling up or ratcheting up of complexity of the behavior, but still even the ratcheted up behavior would stay within the ZLS. And with this, I hope I've given you a little bit of an insight on this hypothesis, and obviously I'm happy to take questions later or also on Slack. Thank you.
Thank you very much, Eva. And that has cleared up a few questions I actually had about the zone of latent solutions that I was too afraid to ask Claudio. So we are going to not go to questions for Eva's talk straight away. We're going to save those for the panel session just after the next talk. But you are welcome to enter any questions you have in the chat, which Eva could go to now if she wanted to, or we can ask during the panel. So everyone else can hear them, and you can enter them on Slack as well if you come up with anything afterwards. So our next invited talk is going to be from James Winters. So James has recently moved to the School of Collective Intelligence at the Mohammed VI Polytechnic University in Morocco, which looks like it's turning into an extraordinarily exciting place to be. Yeah. And before that, I believe you're at the Max Planck Institute as well. So it's quite a move. So if he's a bit tired, I might explain it. So James is described as a cognitive scientist working in the domains of cultural evolution, technology, and communication. James is a modeler. I have live read some of his code, and it was very good. And he writes very interesting models and talks about open-ended cultural evolution quite a lot. So James today is going to be talking about why open-ended cumulative culture is rare. So over to you, James.
Thanks a lot for the introduction. And so let's just get this going. Okay, can you see my slides?
Yeah, can see them perfectly.
Great. Okay. So I'm not going to definitively answer this question, not too surprisingly, but I'm going to maybe hopefully stimulate some interesting thoughts on this topic. To kick things off, a standard cultural evolutionary talk might start out by observing that humans are unique because we've expanded into a variety of ecological niches. So for instance, if we take the Arctic basin, then we'll find that while polar bears have evolved thick layers of blubber, large paws, and specialized carnassials to survive and hunt in Arctic environments, the Inuit have achieved comparable outcomes by modifying and extending existing technologies to culturally adapt by inventing things like parkas, mukluks, and harpoons. And this sort of seemingly unparalleled human ability is believed to follow a basic recipe of generating innovations, socially transmitting these innovations from generation to generation, and also having the ability to select between these innovations to adapt to these various ecological niches. And taken together, these three aspects can, under some circumstances, result in a cumulative growth dynamic, as Eva was talking about. And this is a very old idea, and it's represented in a variety of works that more or less agree on the broad theme, but differ in specific details, as well as what mechanisms they think are important to sort of generating these dynamics. But what does cumulative growth actually mean in these frameworks? Well, perhaps not too surprisingly, this is quite a contentious topic and subject to considerable debate. And colloquially, is captured by the quote, often probably erroneously attributed to Isaac Newton, which states that if I have seen further than others, it is by standing on the shoulders of giants. But this idea of accumulation has been studied far more rigorously in the literature on cultural evolution, where in general, it refers to improvements in optimization, growth in diversity, and or increases in complexity. But one issue is that it's not always clear how these aspects interact with one another and to what extent bounded cumulative growth, which is what we often observe in models and experiments, relates to the open-ended dynamics we actually observe with human culture. And such tensions are evident, for instance, in this excellent paper by Durex and colleagues, where they argue that models of cumulative culture aim to capture an open-ended process that generates increasingly complex solutions. The ultimate goal of these models is to identify the conditions that promote the production and maintenance of complex cultural traits, which is great. But when you look at the model they develop, what you see is the following. The parameters, which we can ignore here, influence the level of cumulative growth, but the dynamics eventually stagnate in the long run. And this is something that is repeated throughout the literature, where it's sort of implicitly assumed that bounded cumulative growth generalizes to open-ended dynamics. But is this assumption accurate? And this is one of the things I want to try and answer. But before I turn to my model that I want to talk about, I just want to sort of talk about another, albeit related issue, which is that even in cases of models that do show open-ended growth, it is assumed that such growth is an inevitability given certain preconditions. And this was explicitly stated in a paper by Kopol and colleagues in the context of the Industrial Revolution, where they state that a remarkably simple model of a combinatorial model of technological change suggests that the Industrial Revolution was a combinatorial explosion in an unchanging process of technological change that began with the origin of our species. In this model, particular causes influence the timing and location of the Industrial Revolution, but not whether it was going to happen or not. So to summarize here, on the one hand, we have models of bounded cumulative growth, which are assumed to generalize to open-ended growth. And on the other hand, we have open-ended models that basically assume this growth is an inevitability once certain preconditions are in place. And I want to try and address or start to address some of these issues using an agent-based modeling framework I've developed called BitWorld, which here I'm going to try and use to address the following questions. So first of all, do the dynamics for bounded cumulative growth generalize open-ended dynamics? And is open-ended cumulative growth an inevitability once certain preconditions are in place? And this builds on previous work outlined in these two papers here, one of which James rigorously critiqued. So as you can see, the model is broken up into 4 central components. I'm going to give you a bit of a whirlwind tour here, but so we have problem solving, solution optimization, problem discovery, and social transmission. And so to focus on the problem solving component, first of all, the basic goal of an agent in this model is to solve problems by generating solutions. So here, problems are meant to approximate the specific challenges faced by individuals, and solutions represent the skills, techniques, or artifacts used to solve these problems. And here, as you can see, both problems and solutions are operationalized as strings of varying length, and each solution is essentially an algorithm that generates a function, which is a bit string, and this function is then mapped onto a specific problem, which is also a bit string. So problem solving is modeled by determining the extent to which a solution efficiently maps onto a problem. And efficiency is measured here by taking the Levenshtein distance between a problem and solution, which basically is the number of edits required to transform one string into another. So in this sense, the most efficient solution is one which has 0 distance between the function string here and the problem string, which would be 0 Levenshtein distance. But in this model, there's a catch. Agents have no knowledge about the underlying structure of the problem. Instead, they rely on feedback about the distance between a function and a problem, and then use this to try and find better solutions via 2 routes, solution optimization and problem discovery. The first of these, solution optimization, solves specific problems by searching the space of possible solutions using both incremental and combinatorial forms of innovation. Here, an agent first generates a set of options to solve a specific problem, and then they basically assign the most efficient solution to their memory, and they do this repeatedly every time step. The second process available to agents at each time step is problem discovery. And this essentially inverts the situation I outlined for solution optimization. Now, here, agents search the space of possible problems as opposed to solutions. And the idea here is that existing cultural solutions can be repurposed to open up novel problem-solving opportunities. So the landscape agents are operating in is a dynamic one and has the potential to expand indefinitely. And to give a toy example of these dynamics, here populations start out by solving problems in the space of 4 possibilities. But unlike many existing models, this space is open-ended. So here the black box represents the current problem, and the gray boxes represent possible problems the population can move to, which in this example are always a single edit away from the current problem, but agents can also leap to more distant regions of the search space. And as the population moves through this space, you'll notice two things. First, the strings get longer, and second, the number of possible moves increases. And importantly, for populations to be able to move in the first place, a solution has to be viable in that it efficiently solves an existing problem where viability is determined by an arbitrary threshold. And I'm happy to discuss that in the questions. But importantly, this mirrors several fundamental properties of problem solving in the real world. The problems are diverse, that they are connected to one another, and that they can vary in difficulty, where difficulty is synonymous with length here. So all else being equal, longer problems are harder to solve because they require more intensive search processes to find an optimal outcome. So this dynamic of optimization and discovery is repeated over a life cycle of an individual agent, which consists of 25 time steps for each generation. And then following these 25 time steps, all agents in the population are replaced by a new population of agents. And during this replacement, agents transmit their currently best solution to the next generation. And this means every agent forms a lineage of transmission. And each transmission episode here is subject to an error rate, which is just the probability of information loss. And it's also an inductive process, which I'm not going to go into detail here. But so that's like, as I said, a whirlwind tour of the model. And what I want to argue is that using this model, we can sort of define open-endedness in a cultural evolutionary context as a process through which populations solve increasingly difficult problems over potentially unboundedly long timescales. And this flips sort of the usual scenario in the cultural evolution literature, where the focus is on changes to the solutions, to sort of looking at this idea of problem difficulty. And in this model, this increase in problem difficulty is represented by the growth of the problem space, but it could also equally apply to computational constraints inherent in increasingly difficult problems, as well as real-world analogs, such as the fact that a person landing on the moon is orders of magnitude more difficult than generating powered flight. So with this definition in mind, we can turn to our first question. Do the dynamics for bounded cumulative growth generalize to open-ended dynamics? And here I'm going to look at just two parameters that influence the dynamics of growth. The error rate, which, as I said earlier, refers to the probability of information loss during transmission episodes, and population size, which is pretty self-explanatory. So standard cultural evolutionary models would predict that growth should be maximized here, where we have large populations and minimal information loss. So if we look at, if we just look at high fidelity transmission, where we have an error rate of 0.05 and manipulate the population size as indexed by the colors here, what we see is the larger populations generally achieve higher levels of difficulty, and the dynamics tend to produce relatively predictable outcomes with very minor variations between runs for a given population parameter. However, as you'll notice here, cumulative growth is subjected to diminishing returns in the long run. And then the reason why this happens is because the dynamics end up in what I've called optimization traps. So here, populations end up circulating around a fixed region in the search space and gradually optimize around a small set of problems. So basically, optimization traps inhibit the ability to generate continual jumpy innovations that are necessary to maintain open-ended cumulative growth. And as a result, incremental innovations dominate the dynamics, as these have a higher probability of improving a fit between a problem and a solution. But essentially, it leads to overfitting and you get stuck. So to answer our first question, it's not so clear that the preconditions for bounded cumulative growth necessarily generalize to open-ended dynamics. And now we can turn to our second question, which is open-ended cumulative growth an inevitability once certain preconditions are in place? So if we look at the entire parameter space of information loss and population size, which is shown here on this heat map, where higher levels of difficulty corresponds to darker colors, what we see is that the highest levels of difficulty are reached by populations where there is substantial information loss, but not too much. And it is in these regions where we're most likely to observe open-ended dynamics. And I think the reason for this is partly because higher levels of information loss introduce flexibility in the search dynamics and stop them from becoming stuck in optimization traps, essentially repeated perturbations. So let's just focus on an error rate of 0.4. And what we see is that the majority of runs are very different to what we observed with the error rate of 0.5. And the sort of standout run here is the one that it seems to have this runaway or open-ended like growth. But before I turn to that run, I first want to zoom in on what constitutes the majority of the dynamics here. And what we see here is that the majority of runs show sort of these arbitrary periods of growth followed by periods of decline or stagnation. And again, growth is generally maximized with larger populations, but it's highly unstable. So if we zoom back out again and focus on this single run where we get runaway growth, why does this emerge? Well, I think it's partly to do with the path taken by this particular run and how through essentially sort of very rare events, it ends up in a sweet spot or a tipping point that unmasks the potential of combinatorial innovation to continually generate a compounding effect of these sort of jumpy innovations. And importantly, this emergent property is entirely endogenous and it's not the result of tinkering with the parameters. And as such, it's not an inevitability of a specific parameter configuration. Moreover, once these open-ended dynamics have emerged, we can ask ourselves, are they maintained? And I think this is important because it might simply be the case that dynamics will collapse in a similar manner to what we observed with the other runs. It just reached further into the space. But we can test this by generating several spin-off runs with the endpoint of our original run as the starting point. And what we see is that these open-ended dynamics are maintained, albeit with a lot of variation between runs. And this suggests something special is going on past a certain point of difficulty. It's just the case that in many of the runs, reaching this tipping point is hard. So maybe there is an inevitability past a certain point of accumulation. So to conclude, there's this implicit assumption that cumulative growth generalizes to open-ended dynamics, and I've shown here that this might not necessarily be true. Instead, parameters that supposedly maximize growth often end up in optimization traps. Moreover, even in regions of the parameter space where we observe open-endedness, emergence is not an inevitability. In fact, it's a rarity. And unmasking the potential for combinatorial invention to generate these leaps requires reaching a tipping point where populations are perturbed and they can generate these jumpy innovations. And I sort of want to argue that this takeoff is path dependent and contingent on the historical path taken by population. And ultimately, I think this might lead to a more parsimonious explanation of open-ended growth dynamics in cultural evolution and specifically why they're rare. So thanks a lot.
That was a wonderful talk. Thank you very much, James. So I'm going to hand over to Simon, who is going to run this panel session for us. So Simon, what are your rules?
Great, thanks, James. So really, I think we can start off this panel discussion. If we have any questions for our three speakers, so Richard, Eva and James, that would be great. And I think we can do it if people could either put questions in the chat, or if you would prefer, just put your hand up in Zoom and then we can go to you and you can unmute yourself and we can have a discussion by voice. So either of those is fine. So please, if you have any questions, just in the chat or just raise your hand on Zoom.
I'll go first then. Come on, guys, this is like first years. So I was going to ask Eva a question that I think James might have partially answered, but I'm not sure. So obviously, primates and humans are about as closely related as you can sort of get, well, ish. But there's this really significant difference in, human and primate cultural evolution. The ZLS plus compared to just the ZLS. What is it, do you think, that led to that jump I mean, that's a big question, and I'm not really expecting you to be able to answer it. Because James seems to be sort of maybe suggesting that a focus on combinatorial innovation rather than incremental innovation or incremental optimization might be kind of the defining kind of adaptation, if you like, adaptations for combinatorial innovation over just kind of basic incremental optimization. But what do you think? What do you think might be the jumping off point to allow this kind of runaway process towards human cumulative cultural evolution?
Yeah, I wouldn't even argue against that. I think this combinatorial innovation is one of the key factors, but for me, it's just like it's a host of processes, obviously, and there has been a co-evolution of like innovative capacities of our ancestors, and also this capacity, or at least the motivation for action copying, right? I mean, we wish we would know what set off what. But like, to me, what I would add to that, apart from the innovative abilities, obviously, one of the other pillars would be this enhanced engagement in action copying. Yeah, but obviously with the innovation, there needs to be something interesting out there to copy. Otherwise, why would action copying evolve or improve? Yeah, so I would add that to the mix. And I have to add also that what has improved or increased in our lineage is probably also this motivation for action copying, not the capacity itself, because experiments with encultured great apes show that they are capable of action copying, like if you train them enough, but obviously they are not very representative of the wild great apes.
Great, thank you. And we have a hand up from Jan. If you'd like to unmute yourself, please. Or I can do it for you, I think, possibly. Or can I? No, I can't.
There's a problem with his mic, so I think he's typing out his question.
This is a lot of pressure on Jan, just staring at him typing. Oh, he says, keep going, I will ask later.
Okay, and we have a hand up from Tom.
Hi there. Yeah, this is a question for Richard Watson. I am not from the discipline of arts visual life or any of this stuff, so it was I felt a bit out of my depth listening to the talk, but so I just wanted to like clarify a little bit, kind of the ideas in your talk. It seemed like you were attempting to sort of formalize why like meta level organization appears in like competitive or environments consisting of self-interested agents, and explaining that as basically the relaxation of frustrations, I think was the phrase you used, in that it's kind of at a meta level they're incentivized to decrease the extent to which they compete in some respects. Would that kind of be am I barking up the wrong tree there, or?
That's a great start, yes. And I think that, to be fair, I was probably going a bit quick and putting a lot of information for anyone in the audience, so don't worry about that. Yes, I am trying to understand how a system can create adaptive organization above the level of the individual. But it's a little bit more of a bigger ask than that, because other people have said, well, don't look for that because it isn't possible. There can't be any mechanism that produces adaptive organization bigger than the individual. So I have to show that it's possible, that there exists another adaptive mechanism, and then show that that could be implemented. It could be a process that could produce adaptation at a level above the individual. And the mechanism requires the differential easing of frustrations, the changing that it's individual self-interest, short-term individual self-interest motivates individuals to ease their frustrations with others, and that's differential in the sense that some frustrations are more important to them than others. But that's not quite the whole algorithm, because you could do that without the perturbations, and if you did, you wouldn't get any optimization, you wouldn't get any adaptation. All you'd get is a system that the state variables quickly relax, and then the interactions slowly relax, and you just end up with a system that's stuck at whatever the first thing it did is the only thing it can ever do. So with the perturbations, that gives you a distribution of local optima, and because it's learning correlations, it can generalize, and that's what produces the optimization. So that doesn't have a name, that's a new algorithm.
Okay.
Well, it does. I call it adaptation by natural induction.
Okay, so it's some form of stochastic optimization, but the interest is that this is a natural process. You know, that you have this kind of stochastic constraint-based optimization in natural systems.
Yeah, it has a stochastic element, but not in the same sense of simulated annealing, for example. It's more like a learning neural network, which you can do deterministically.
Yeah, okay.
You have those occasional resets, but yeah.
Yeah, okay. I think my unfamiliarity
understood perfectly well. Thank you, Tom.
With like a little bit of my understanding as well. So, okay, yeah, thank you. That's well, one of the things I wanted to say was that it seemed a little bit like you were kind of trying to sort of butt heads with Darwinism in some way, or at least with like natural selection as the evolution mechanism. But it kind of felt like at the end you were discussing something bigger, in the sense that I don't know how to phrase this. By the end, it didn't seem like, it felt like you're working at a different, I mean, explicitly said yourself you're working at a different level, and therefore it wasn't really clear to me like how the claim that natural selection is the only adaptation mechanism was as relevant as it could have been by the end, because you'd kind of moved to, you'd zoomed out in some way, and by that point, like the concerns of agents were less. I think you said yourself that individuality also becomes more fluid, but from the perspective of an individual, it's hard to see how that's, you know, I guess a useful conclusion to somebody in the system. Like, if we're going for a grander kind of social thing, how, to what extent is this relevant to the, you know, the libertarian like economics? Yeah.
Thank you. So, I mean, this is versus ought stuff, right? So you can describe what happens in a system, but that doesn't mean that it's a good thing to happen or that it ought to happen in a system, right? And there's also a notion of, do the components in the system have any awareness of what's going on at the system level? Do the cells of a multicellular organism know that the context that they're in creates an organismic structure at a higher level of organization? Or from their point of view, do they just know, well, I'm here and this is my environment and this is what I'm doing, and I'm doing it for my own self-interest. I'll reproduce as much as I can, even though I'm going to die if I'm not in the germline. So we could take an attitude that people in society, well, just carry on then. Just carry on being self-interested, just carry on maximizing your individual interests in the short term. And we may step back from that and notice that the social structures are becoming organized through induction over time, but the individual doesn't need to know that. That's something which happens at the system level. However, If you're going to take an attitude that, well, we understand everything that could be happening at all levels of organization, and we as individuals are the highest level of organization that can have an intention or be an individual, then we can decide that there isn't anything of which we are a part. There's just disorganization, unorganized system in which we are a part. There's nothing to be concerned about if you were to exploit it or treat it as resources, or to be unkind to it, because there just isn't anything there. It's just us. We're the biggest level of organization there is. But if you have a framework that permits the possibility of organization that's greater than the individual, then perhaps it could engender a different attitude towards it. You can still say, yeah, maybe that happens, but I don't care, right? But if you're going to take an is versus ought attitude towards Darwinism and say, for example, that selfishness is a virtue, then because it facilitates adaptation by natural selection, you don't want to mess with that, because natural selection or individual self-interest is the only way to produce adaptation. If you're going to do that is ought there, then if your science is wrong, you're doing the wrong ought, right? If the way in which it works is different, then what you'd need to do in order to enhance it is different.
Yes, I had a similar thought towards the beginning of the talk when you discussed, when you went over the kind of, is being selfless actually being selfish, which I find a kind of almost nonsensical argument, because it doesn't really have any kind of normative conclusion, because you could, you're basically then falling into whether or not actually being selfish or actually being selfish is the most efficient way of being selfish. It doesn't, to some extent, yeah.
Yeah, that's right. So that's why, it's because I struggle with that, because, you could say, oh, so wait a minute, so what's happening then? If the adaptation at the system level is produced through being self-interested anyway, then the logic of self-interest isn't challenged, even though natural selection produces, natural induction shapes the structure of natural selection. The logic of self-interest is still sound. But I think the only way that the logic of self-interest can be challenged is to challenge the concept of individuality, is to say that the individuals in the system aren't clear, the utility functions in the system aren't clear. And when you start to mess with that, now it might still be true that if you had an individual with interests, it would be logical for it to maximize them, but it's not really clear what it is we're looking at now. We're looking at a dynamical system that has a behavior at a higher level of organization. It's not necessarily illogical or correct to think of that as an agent that's doing maximization.
Okay. Thank you very much. I will.
Great questions. Thank you.
Great, thanks, Richard. I think Jan, yeah, cool.
Yeah, let's give it a shot. Can you hear me?
Yeah, that's fine.
Okay, yeah, I would have a question for Eva, maybe building upon your question, James. And I don't know if you can really answer that, but do you have any idea around what period in human evolution humans started to escape the zone of latent solutions? Was it that cognitive revolution? Was it prior to that? Do you have any idea?
That is a very good question. Actually, Claudio is working on a grant at the moment, finding out exactly that. So he basically says that the older one stone tools, so basically the first set of super simple stone tools that you find, are still within the zone of latent solutions. Obviously, the archaeologists are not so happy about, or many of them are not so happy with this explanation, but he is trying to find out whether this is true. And this would actually mean that, and the reasoning for that is he's trying to explain the stasis that you see in the archaeological record. Obviously, I mean, we only have the stone tools left. We don't know so much about the non-lithic artifacts, but he's trying to say that one reason for the stasis is because it's latent solutions actually, and then only later on the more sophisticated tools require this action copying. It's still in the phase of being tested, but I can refer you to his most recent work where he's trying to exactly pinpoint that. Yeah, so I don't know whether we can put like blah, blah, blah million years yet. But yeah, that is a very hot topic question.
Yeah, just maybe, I don't know if you're allowed to say anything about that already, but do you currently think it's rather like cognitive revolution, like 10,000 10,000 years ago, or is it much earlier than that? Do you have any clue, or is it still really?
I think personally, I think it would be a bit earlier than just 10,000 years ago, because I think there were just precursors that we might not see. But for that, I'm not too much into, like, I'm not an archaeologist. So yeah,
I know it was a tricky question. I was just wondering. Yeah.
Yeah, I think it is a bit earlier than that, because it has precursors. But yeah, that is still an open question, more or less.
Yeah, speaking of, I think cognitive revolution is also thought to be rather 20, 30,000 years or something. I don't know. I'm also not too much into it, but yeah. Interesting. Thank you.
Yeah, well, thanks for the question.
Well, thank you. And I think we have a question from Stavros next.
Hi. So this is a question about natural induction, but I want the question I'm about to ask based on it addressed to all the panelists. So natural induction is this like really interesting sort of A-lifey idea, but in terms of grounding it more in mechanisms of cultural evolution, a bit more of the empirical stuff, I was thinking, if a system that perturbs itself more, the reason that will have more than a few factors, if that makes sense. Sort of, I'm looking to Richard to see if he agrees with me.
I'm sorry, something I missed a bit there. Could you say that?
That's okay. So if a system that's perturbed will have a chance to experience more attractors, I know I'm personifying it now, but just for the purposes of explanation, if a system somehow manages to perturb itself more through some mechanism in order to, it can, cycle through more attractors and maybe induction will work better. Sort of that sort of abstract thing I've sketched. I was wondering if between all the panelists and anyone else, if they can think of a sort of cultural or biological system that does that, which I know is a bit of an ask, but I thought I would sort of air that question.
I would love to hear the other speakers help me ground it in the way that you suggest, if they can.
Sorry, I missed it. Sorry. My connection's super bad for some reason. Could you just have one more go, just saying what the question was?
Yeah. So the idea is, given the mechanism of natural induction, one of the requirements is that the system is perturbed to state, so it will, relax again. I think it was at another attractor. So it stands to reason that the more perturbations of the system you have, the more time it will have to settle at different attractors and experience even more attractors and maybe arrive at a better solution by the end of it. So I was thinking, given that that's quite an abstract A-life idea, does it make sense so far? Do you want any more exposition or?
No, that seems clear to me. Yeah.
Okay, yeah. So if there's an example of this sort of perturbation mechanism that we can think of in about either a cultural, biological, or socio-biological system that does that.
Yeah. I mean, I suppose, like, actually in the model I presented, the main source of perturbations are actually coming from the transmission mechanism. So actually the transmission of social information from one generation to the next. And it seems like, in my model anyway, at least, it seems like that's quite an important mechanism for driving the exploration or the discovery dynamics. So at least, like, from my perspective, perturbation is from the transmission mechanism, but it could come from other things like maybe increases in population size, for instance. So if you have larger populations, essentially you've got more instances of information exchange, and that can also perturb the dynamics because you have multiple sources you need to learn from. And this is definitely the case as you get more complex cultural traits, you need to learn from multiple sources, probably, almost certainly. That's still a bit abstract. It's not really grounded in a specific cultural phenomena, but it's sort of trying to get at maybe some mechanisms that might translate from Richard's work over to cultural evolution. And also, I would say as well, partly, I think the perturbation works well in transmission systems because human transmission isn't, it's an inductive process, right? So you sample from the behavior of someone else, and then it's not always like essentially you try and reconstruct in your mind the behavior you're trying to learn. So it's not this passive process of just copying from one individual. You're actually taking in information, and maybe having information that's slightly lossy allows you to make better inferences, which is what we would be the take-home message from just any sort of instances like statistical modeling and stuff like that, where you have some sort of induction mechanism. So, yeah.
So would, just quickly to add on to that, would sort of cultural drift and genetic drift do similar things, sort of?
Yeah, right.
If a massive random events resets, that sort of sounds like Richard's idea, I think. But yeah, thanks for your answer.
Thank you. In some of the gene network models, we model the resets as a period of drift, of genetic drift in the absence of selection. So there's periods of episodic selection, like repeated exposure to a stress environment or repeated exposure to a predator, which drives change by natural selection. And then in the interim periods, there's drift, which is then the next stress, the next episode, you begin from a new random initial condition, but the gene regulatory network inherits the connective structure. The way in which a system, the way in which biological systems create their own perturbation so that they can have multiple experiences is by making organisms that have life cycles. So when you have a life cycle, you get back to like a saddle point in the dynamical system at the early embryonic stage of development. It's like anything can happen in your phenotype. You're back to a point which is sensitive. You're back to a saddle point. And from there, small changes in the interaction structure can guide you into different attractors. But if you didn't repeatedly go back to that saddle point where all of the gene expression dynamics are leveled out and you're right at this sort of neutral saddle point, then the evolving correlations wouldn't be able to push you into different attractors. So when a life cycle, when a living system generates a life cycle, that it's not just existing, but existing in a way that goes back to, let's level everything out, flatten everything off and have another go, right? The next generation, that's doing those perturbations in that system. But a more amusing answer is from Tom Froese. Some of you might know. I'll put his papers in the chat. He says we should have more parties. We should go out and get smashed more often. And we should do it in a big cultural party where everybody gets smashed at the same time. And I like that quite a lot. So the ancient Teotihuacans, something like that, they used to have lots of parties, apparently. Everybody used to get totally wasted. And they had, didn't seem to have any centralized governance, but did seem to have quite a lot of technological advancement. So you might like to have a look at those papers.
Great, thank you, Richard. Fascinating discussion. I should probably let people leave to go to the keynote talk for the A-Life conference now that's just starting, which is Jessica Flack. So that's relevant for us. Thanks to the three speakers. That was a fantastic session. We'll be having the second session straight after the keynote. There were a few questions in the chat I think we've not got to, so I'll copy those, paste them in the Slack, and if speakers could answer them there, that would be fantastic. So we'll see you all in 1 hour's time.
Thank you very much, everybody. Thank you very much, Simon.
Yeah, thank you, Simon. Thank you, James.
It was great. Thank you very much, everybody. I really appreciate you all coming.
Thanks, James. I'm signing off for today. I really appreciated the opportunity to speak. Thanks.
Hope everything goes
really
well.
Great questions.
Have a great night.
Thanks.
Thanks, bye.